Okay, welcome back. Chapter 3, page 51. We're in steel making processes. We're going to jump over to the cementation process. Okay, here just talks about the different processes that are used within steel making. We're going to break them down individually and go forward. The oldest method of steel making is the cementation process. Consists of heating wrought iron with carbon in a vacuum. So let's read from the book, page 51. Bolded item, cementation is the oldest method of steel making. It consists of heating wrought iron with carbon in a vacuum. This increases the carbon content of surfaces and edges, which can then be hardened by heating and quenching. The metal is not molten during steel making. Hence, impurities are not removed from the iron, and only the surface of the metal is affected. It is probable that most of the steel of ancient times was produced in this way. We'll get into you get into the weld inspection portion. We start talking about interstitial and substitutional alloying and case hardening and so forth. And this is very similar to what we were talking about with the sword process. It increases the carbon content of the surface and the edges. So, you know, older ancient times where you were running the steel on top of carbon helped produce the carbon within the edges and leave the outer layer of it very hard. Carbon was absorbed into the material. And this created better swords because it would harden them, make them sharper, a little more durable, and so forth. Okay? However, the impurities in the center wasn't melted 100%. The impurities in the center were not removed, and only the surface is affected. To a certain extent, we can always break that down a lot more in depth as far as metallurgical, because it is usually above the lower transformation range when that happens. Okay? And we'll talk about that later on. Iron carbon phase diagram, items such as that. The later process is layered soft and hard metal for strength. So this is very similar. We'll talk about cementation. And then on a microscopic scale, it is essentially like laminate woods or other materials as well. What they found out is instead of making it, you add some strength and ductility by putting a soft material in between hard materials. Okay? So for example, if a very microscopic piece, if we have a sheet of steel and then the same size sheet of a pillow or something that's softer, what happens is it can give and take a certain amount of material by doing that, layering it. And that is some of the cementations where you have ferrite and iron and so forth within it. Okay? All right. The crucible process, I'm going to read from the book. It's a melting pot, okay? Creating a crucible or a pig iron, so to say. The crucible process was revived in England during the early 1740s. Steel produced by the cementation process was melted in a clay crucible to remove the impurities. While fluid, the slag was skimmed off the top. Then the metal was poured into a mold where it solidified into a mass that could be worked into the desired shape. In the United States, graphite crucibles with the capacity of about 100 pounds of metal were used in a gas-fired furnace. This process produced a steel of uniform quality that was free of slag and dust. So, this again, we start talking about inventions and how they still hold true today. The basic physics are never going to change, okay? In the majority of the trades. The concepts of physics and limitations will always be there in anything we do, okay? So for example, the 1740s, they found out that, that by melting the steel, you can remove the impurities within, all right? When fluid, the slag was skimmed off the top. This is the exact same thing that all welding, electric arc welding processes do today still, correct? Is that we make sure that that liquid puddle is fluid so it fuses together, it combines, and then the slag is pulled off of the top. The impurities are brought to the surface, whether it be by a gas shielding or by the flux itself going forward. And then also what we found is that at this point is our best chance to add alloying elements to improve qualities as well. Because what happens is it's just like many other things, if we regulate how much we put in, it disperses evenly in a liquid form better than it would in a solid form, okay? So the majority of our alloying out of our we talked about our flux and our slag on our shielded metal arc welding electrodes and our flux core arc welding wire is done, the majority of that alloy is done out of the flux. So it's melted, added to the fluid so it disperses evenly, finds its home position, bonds with other chemicals before it solidifies, and if it doesn't, then it's considered an impurity and it's brought to the top and skimmed off, all right? Then it's poured into a mold to solidify into a workable piece. Same thing. Same thing still done today. Okay. Electric arc processes, page 53. Okay. Electric furnace processes. Electric furnaces are of two types: the electric arc type and the induction furnaces. That's a bulleted item out of the book. I'm going to skip over to the right-hand column, bottom paragraph. It starts out, electricity is used solely for the production of heat and does not impart any properties to the steel. These furnaces have 3 electrodes ranging from 4 to 24 inches in diameter. They produce a direct arc with 3-phase power and are supplied with electric current through a transformer. Newer furnaces have electric capacity between 900 to 1,000 kilovolt amps per ton of steel being processed. This could amount to 42,000 amps, thus a very high energy arc. Keep this in mind next time you're welding at 100 amps or less, okay? Let me finish this paragraph and then we'll talk more about the slide. Page 54, we're continuing on, okay? The electrodes enter the furnace through the roof. The roof is removable and can be swung aside to charge the furnace. The charge consists almost entirely of scrap with small amounts of burned lime and mill scale. The furnaces are circular and can be tilted to tip the molten steel into a ladle. And you can see some pictures there on that. Okay, let's look at the PowerPoint slide here. French metallurgist Paul Hérault in 1899. These dates aren't necessarily important for the test, just kind of interesting to know. Produced more than 800 tons of steel in 24 hours, so we really ramped up production, so to say. Electricity used solely for production of heat. Again, it does not add anything to the steel making process that I know of as of lately even. I haven't heard of anything or read anything like a shock treatment or anything that stress relieves, anneals, or anything like that. The only reason that we use electricity for it is to heat it up, that I know of. Okay? Okay, so here's one electric arc furnace. Okay? The electric induction furnace. This is more of the common type today. Let's find it. Page 55, right-hand column, second paragraph down. The electric induction furnace, figure 3-15, you can flip it, it's on the next page, okay, is essentially a transformer with a molten metal acting as the core. It consists of a crucible, usually made of magnesia, surrounded by a layer of tamped-in magnesia refractory. Around this is a coil made of copper tubing, forming the primary winding that is connected to the current source. The coil is encased in a heavy box with a silica brick bottom lining. A lip is built into the box to allow the metal contents to run out as the furnace is tilted forward. The charge consists of scrap of the approximate composition desired plus necessary ferro alloys to give final chemical compositions within specifications. Scrap may be any size that will fit into the furnace. So especially in modern day times, as we get, you can cut bigger pieces of scrap to go in the furnace. It's easier to load in than having to load it through the top and so forth. We are down to being more lean and more efficient, okay? The charge can be melted down in 45 minutes. You can, in the liquid form, you can have alloys and deoxidizers add them at an even rate. And then it can be poured out as well, okay? So right here is the bath of molten metal. Right here, your copper tubing within the vessel. Your pouring spout right here. You can look this up online as well. Just Google in electric induction furnace or steel making induction furnace. Some pretty neat videos out there of how things go or how they are used, and give you a good idea of that. My grandfather worked at an Elger factory to where they cast their own bathtubs, the old cast iron bathtubs. He worked in the furnace room. It was, I believe they called it piecework at that time. You're around several thousand degree heat all day working around it. So you would sweat. You were only allowed to work in that type of environment for about 5 hours at a time. He used to say that if somebody wasn't sweating, it was like kind of like being in a atmosphere without any oxygen. It was alarming. Okay, you had to get them out of there because they were more than likely already dehydrated, and they needed to go sit down before they got really, really sick or fainted. He said he remembered a certain situation to where the materials supporting this, the chain supporting the ladle, broke. They weren't properly maintained. Everybody just kind of went past them. They didn't do a routine check. And one of them poured out one time, and it completely burned one of his co-workers' leg off. All right. So, very important to be careful working in an environment similar to this. Oxygen processes. I'm going to let you read about this on your own if you want. Kind of an interesting concept. What happens here is they introduce oxygen within it to help heat it up and support combustion. Remember, it does not burn on its own. Helps, they believe that this was one good way to help pull more impurities and kind of agitate the molten metal to get the impurities and the slag to come to the surface. Okay. Vacuum furnaces and degassing. Page 57. I'm going to read from the book. Left-hand column, bottom. The melting of steel and other alloys in a vacuum reduces the gases in a metal and produces metal with a minimum of impurities. The gases formed in a vacuum furnace are pulled out of the metal by vacuum pumps. The advantages is freedom from the air contamination. So you can imagine we've talked about porosity, and you'll get a one solid weldment is what you're hoping for. You can have a closer control of heat because you don't have outside air influencing and helping support combustion. And there are fewer inclusions, like you said, with porosity. So on page 60, we're going to go to page 60. And talk about this. Top diagram talks about vacuum processing of steel. Steels for special applications are often processed in a vacuum to give them properties not otherwise obtainable. The primary purpose of vacuum processing is to remove such gases as oxygen, nitrogen, and hydrogen from molten metal to make high purity steel. Many grades of steel are degassed by processing similar to those shown in this page. Even greater purity and uniformity of steel chemistry than is available by degassing is obtained by subjecting the metal to vacuum melting processes like those shown on the page, on the facing page. Go down to vacuum degassers, halfway through that paragraph there, page 60 again. The sentence starts out, make sure we highlight and bullet item. The conventionally melted steel goes into a pony ladle and from there into the chamber. The stream of steel is broken up into droplets when it is exposed to vacuum within the chamber. During the droplet phase, undesirable gases escape from the steel and are drawn off before the metal solidifies in the mold. So there's your pony ladle, okay, your furnace, your pony ladle, so forth. Page 60, bottom left. Ladle degassing facilities of several kinds are in current use. In the left-hand facility, molten steel is forced by atmospheric pressure into the heated chamber. Gases are removed in this pressure chamber, which is then raised so that the molten steel returns by gravity into the ladle. Since not all the steel enters the vacuum chamber at one time, this process is repeated until essentially all the steel in the ladle has been processed. Quite an interesting concept. So as what you can see here, it's kind of what we're talking about, a vacuum lifter. Vacuum's created here to help pull. Atmospheric pressure naturally exists on this, so with the vacuum here it will bring it in. Gas comes out through here, okay? All right, benefits from degassing. Read through these. We just talked about them. We read from them from the book. Continuous castings of steel, page 63. I'm going to read from the book. The continuous casting is a process by which molten steel is solidified into a semi-finished billet, bloom, or slab for subsequent finishing. So there it goes back to those three items: billet, bloom, or slab for finishing. Okay, the prior method was forming ingots. So instead of just doing ingots, now they are actually putting them into specific shapes for a specific use. And we'll see here in a minute what they, whether it be like a plate or I-beams or square round bar and so forth, which ones they use, okay? Improved yield, quality, productivity, and cost efficiency. Various shapes are cast. Complete operation can be achieved in 2 hours. So this slide right here is on page 64, right-hand column, halfway down. The paragraph starts out, depending on the product end use, and it finishes down there with it can be achieved within 2 hours. Highlight this entire paragraph to remember. Read through the book. Casting process sections. So we're going to go to page 66 under solidification, casting and soaking of ingots. Okay, right-hand column. If molten steel were to be cast into molds having the shape of the desired product, we would always be dealing with cast steel in our structures. Since cast steel is generally inferior to wrought steel, parentheses, metal that is to be worked mechanically, the molten steel is poured into ingot molds or continuance casting and allowed to cool until solidified. To give the inside a chance to become solid and still keep the outside from cooling off too much, the ingot is lowered into a furnace called a soaking pit, which heats the steel for rolling. Figure 3-27 on your right-hand page there illustrates the processes used in solidifying steel. I'm going to read down page 66 under deoxidization. In most steelmaking processes, the primary reaction involved is the combination of carbon and oxygen to form a gas. Proper control of the amount of gas evolved during solidification determines the type of steel. If no gas is evolved, the steel is termed killed because it lies quietly in the molds. Increasing degrees of gas evolution result in killed, semi-killed, capped, and rimmed steel. Okay, go down to the bottom paragraph on that right-hand column, or the second from bottom, called capped steels. The duration of the deoxidization process is curtailed for capped steels so that they have a thin, low carbon rim. Okay? That's the main thing I want you to remember. They have a thin, low carbon rim. The remainder of the cross section, however, approaches the degree of uniformity typical of semi-killed steels. This combination of properties has resulted in a great increase in the use of capped steels over rim steels in recent years. Down to rim steels have the surface and cold forming characteristics of capped steels. They are only slightly deoxidized so that the brisk evolution of gas occurs as the metal begins to solidify. Here's the important bulleted point, is the low carbon surface layer of rim steel is very ductile. Okay? So it can be easily drawn or put through rollers,